So today, after dealing with the problem, the sort of classic problem of fair division, yesterday I'm going to look at another family of models which are, in fact, rather different in their characteristics because they are generally under the title of cost and surplus sharing, where the issue is the sharing of some kind of externalities in production. So, in other words, the key object in that in those models is this cost function C, which you can, of course, it's written here as a cost function. It could be written as a production function as well, but we're going to stick to the cost sharing, the cost function notation. And what this cost function represents is what it's going to cost to serve a bunch of users, of common users of the technology, who may be requesting different amounts of output. So this technology is really the commons is really the thing that they are jointly exploiting. I mean, they are jointly entitled to deal with that technology. And but the externality, namely the complexity of how the C function depends on the various input, is in principle arbitrary, and therefore you have a complex situation where the increase in the demand of one person can have very negative or very positive side effects on the other participants, and we need to find a proper way to take that into account and reward them or punish them. Okay, so the function C is known to the system designer, and so are the demands. And the first thing we're going to discuss very briefly, really, because it's the part of the theory which is probably the best known, is how to deal with this as a pure fair division problem when there are no incentives around, and that corresponds to the terminology that in economics that we call inelastic demands. And what that means is that you have these agent I would like a certain amount of output xi. I mean, here at this level of generality, xi is any request for some output, and this is a known fact, and he's going to pay whatever you charge him or her. Right? She's going to pay whatever is charged. So the demand is inelastic in the sense that there is infinite willingness to pay if you want, and the issue is really how much is it fair to charge to this person. It's not going to affect. Of course, the next stage would be to take into account the elasticity of demand, which means that depending on how much we charge to this person, he's going to want more or less of the commodity. And that's where the economics and the efficiency issues come into play, right? But in the first instance, for the first sort of level of models, all you have is the C function and a list of demands xi, and you are supposed to divide this total cost between the participants, right? So it's a way of expressing responsibility. You know, how does the responsibility of each agent for his own demand translate into a share of the total cost? All right. So the way we do that typically is by looking at counterfactuals, namely. By looking at the entirety of the cost function to determine how to share the cost at a particular level of demand xi, x1, xn. Right? And so the examples, I will probably not have time to do that, but here is is going to be this first type of models, which in fact are rather known. I'm sure most of you already know what I'm talking about. It's just that maybe I'm presenting it slightly differently. So that would be the axiomatic analysis of fairness in this distribution of cost. And so you have to assume inelastic demands for this to make sense, because you want that, you're not looking at the impact of your particular cost sharing rule on the demand of the mechanism. This model is very well developed for the case where the demands are simply 0, 1. For the case where you are talking of a commons, a technology which provides service, for instance, a connectivity, connection to the source, or this sort of examples, and you have a cost function C, which therefore, since each demand is 0 or 1, the cost function C is simply a set function, right? And for each subset of agents that you want to serve, C of S is how much it would cost you to serve them. And of course, this is the model of TU, the well-known model of TU cooperative games, and this is exactly the branch of TU cooperative game theory which is purely axiomatic. The branch that develops concepts such as the Shapley value, the nucleolus, the data array solution, and so forth. And a slightly more general type of models, which is well understood and give rise to a substantial literature, would be an extension where the demands are one-dimensional. So when the demands are one-dimensional, so xi is either an integer or a real number or positive real number. The difference between the two is mostly technical, and some of the models work better with integers, some with real numbers. But we don't really think of these two models as being different. And then you have a cost function which could be of the simple form, what we call homogeneous demands, namely you simply have a one-to-one cost function which takes into account the total demand. That's the simple case to start with. Or more generally, a cost function which is depends arbitrarily of the n component. So I will not have time to review this literature, in particular the extension to one-dimensional demand. You will simply see some of it appearing in the discussion of the mechanism design aspect, and you will get a sense of it. Okay, so that's going to be one thing we're going to survey very fast. Let's keep that. The second goal on which I will concentrate today is really a mechanism design goal, and it's to try to achieve efficient usage of the commons. Because so we have these commons, we have this technology which will correspond to certain demands by the agents, and we would like then to exploit it efficiently, and at the same time, of course, this implies that they're going to have a way to share the costs of the production and to adjust their demands to their own utilities and to the cost-sharing rule. So here you have immediately this interaction between the cost-sharing rule and how it will affect their level of demand and how it relates to the potential efficiency or not efficiency. So here we're going to immediately adopt an important simplifying assumption, which is the quasi-linearity of utilities. And this is not, strictly speaking, you can do quite a bit of the theory without that assumption, but in fact all the important ideas are there already with that assumption, so there is no need for extra complexity. So therefore I'm going to assume that essentially the utilities will be agent I will have a utility of the form ui xi minus yi. Xi will be his demand of output, and yi will be his cost share. Right? And the constraints, which I will retain for most of the talk, and I will explain at the end what can be done if we don't get this constraint, is the standard budget balance, namely that the sum of the cost share has to cover the cost of production, right? And so the thing which is, I absolutely public knowledge in this theory is the cost function itself. I mean, that's a known thing. The utilities, not necessarily, because they are the private preferences that will be revealed through some kind of mechanism. So there is really an incentive compatibility issue. Okay. So because of the quasi-linear utility assumption, we know that efficiency is equivalent to maximizing total net surplus. I said here total utility is probably better. It would be better to say total surplus, right? Efficiency is simply to solve the solution of efficient allocation max over x1 xn sigma I equal 1 to n ui xi minus xi, right? Because we have quasi-linear. Remember that quasi-linearity assumption not only implies that your utility is linear in money, but also what you have what we call deep pocket, namely it's okay for you to borrow or to borrow any amount or to receive any amount. So therefore any allocation which does not maximize this expression is Pareto inferior to an allocation that does maximize the surplus. Okay. Now, of course, the interesting thing will be that the efficient surplus, which we obtain in the equilibrium of whatever mechanism we are looking at, can be compared to the efficient surplus. And this is exactly a benefit of the quasi-linearity assumption, because if you didn't have that, you could still make some statements comparing, some statement about the welfare improvement from the equilibrium to the Pareto frontier, but it would be a lot more delicate technically. Okay. So, all right. So in principle, we would like a mechanism of which the equilibrium divide the cost responsibilities fairly. I mean, we want, that's the fairness requirement, because we want participants to agree to the mechanism. I mean, at the fairness level, I mean, it's a correct way to divide, to assign responsibilities, and if possible, to reach as efficient as possible, I mean, to reach the efficiency frontier. Okay, now, in this theory, we will have, at the same time, if you want, two types of mechanisms or games. Because, and that's a very important restriction in the modeling. Okay, so suppose given a certain cost function here, I have chosen a cost-sharing method. So what I call a cost-sharing method is a systematic way to divide this cost given a list of demands. So this one, we simply think of it as, maybe we can write this as psi I of yi and then comma the rest, the other demand, and then C. And so my cost-sharing method can depend on the entire technology and on the profile of demands. It's some formula, it could be some Shapley value, some simple average, whatever, but we have chosen, we will determine once and for all these cost shares. This is the only instrument in the hands of the system manager. I mean, the system manager here is not going to try to do some Bayesian estimate of where the demands could be and so forth, or anything very fancy like that. He's simply going to say, okay, well, I would like to divide cost by this formula, and let's see what gains this induces. Because once we have such a formula, we have a game. We have a non-cooperative game in which the strategy is xi for agent I. I mean, the demand, that's what we call the demand game. I demand a certain amount, other people demand a certain amount, utility results, that's your game. And we can think and look at the equilibrium of this game. So a cost-sharing method defines a demand game, right? Now, if it happens that this demand game has a unique equilibrium for certain types of cost function and utilities, then this unique equilibrium allows me to define a direct revelation mechanism. So again, this is an important point. So if you think cost-sharing method, it gives you immediately a demand game, a very simple demand game where your strategy is one-dimensional. All the models we look at here are one-dimensional, 0, 1, or positive number. And there may be an equilibrium which is a list of xi, and of course a list of yi star. Now, if the equilibrium happens to be unique, some sort of equilibrium, whatever, it doesn't have to be just Nash, it could be strong equilibrium. In fact, in some model it is strong equilibrium, or maybe others. So once we have a unique equilibrium for any profile of utilities, then we can define a direct revelation mechanism where the planner asks agents to report their utilities and computes, given their report, it computes the corresponding equilibrium and implements it. Right? So, of course, nothing tells you a priori that this elicitation process will be truthful. But the point is that in very important cases, when this equilibrium is unique and, as we will see for, with appropriate assumptions on the technology and the utility, then it will be the case indeed that this elicitation process is absolutely strategy proof. Not just strategy proof, but even group strategy proof. Strategy proof is a deviation by coalition. So we can then therefore think of the two things, the two types of mechanism in parallel, and one is the demand game becomes, if you want, a practical way to implement the thing. If we don't want to ask participants to report this complex object, which is a full-fledged utility function, but it's also possible to think of it as a classic revelation mechanism. Okay, but now there is also a converse way, which is very important in the proofs, which is that under appropriate extra assumptions that we will come to later, a strategy proof mechanism, that is to say, any kind of elicitation process, any kind of direct revelation mechanism where you ask agents to give you their utilities, you then implement some allocation of both output and cost shares. Any kind of mechanism which is strategy proof, which induce dominant strategy to reveal truthfully, that one will have to come from a specific cost function, a specific cost sharing group. So that's a more subtle point, and the fact will be that if in this elicitation process you have some agents which you choose some cost shares for a certain list of demands, then anytime you will implement the same list of demand, you must implement the same cost shares, which is not obvious at all. I mean, it's not something that you can assume, it's something that you will have to prove. Okay. All right. Now, just as a starter to see why we are so interested by strategy proof mechanism, because from the lecture yesterday you could get the impression that trying to get something strategy proof and reasonable is a little bit crazy. But in fact, in this model, group strategy proofness, or at least the weak form of group strategy proofness, where you only require that no coalition can find a way to strictly improve the utility of all of its members, that's clearly within reach, because consider the simple standard fixed priority incremental mechanism. I mean, I don't know what, it's a well-known thing that everybody has or was ever thought about those problems, has thought about it before. It's simply, okay, we remember my my mechanism here, my cost share. So let's play the following mechanism, and I'm going to play it either as a demand game or as a revelation game, and you will see that it's exactly the same thing. So let's play it as a demand game. I have my list of players, and I ask the first, okay, you are paying full cost. You are paying C of x1, 0, 0, 0. How much do you want? Okay, so it tells you what, given that, I want, because I'm going to pay that, so I have to maximize U1, x1 minus C of x1, 0, 0. Okay, this is how much I want. Then you go to the second person and you say, okay, now you're going to have to pay the incremental costs above and beyond what the first guy has already demanded and obtained. I mean, this is the deal is done for x1, so now he has to pay C of x1, x2, 0, 0 minus C of x1, 0, 0. So how much do you want? You, player 2, he maximizes this, he tells you how much, and so forth. So you can see that here the equilibrium is perfectly, I mean, every kind of test of strong non-cooperative equilibrium you can apply will work here, dominance, solvability, whatever. It's also clear that as an elicitation revelation mechanism, it's perfectly strategy proof and even weakly group strategy proof, because you can, instead of having them play the demand game, you can simply say, send me a description of your U1 and I will do the optimization for you. And you have no incentive whatsoever to misrepresent, right? And you cannot even misrepresent as a group, because if you could have here a manipulation by a group would be that the first player, for instance, is indifferent between buying 1 or 2 units at this cost, but if he buys 2 units because marginal costs are decreasing, that's going to help the second guy. So at no cost to myself, I can make life of the second guy a little better. But you see that it's a manipulation of the type, I'm indifferent and he's strictly better off. If you want a manipulation where I'm strictly better off and he's strictly better off, you cannot do it. Okay? So, yes?
So to use this mechanism, it seems like it's not necessary that everything to the right of you be filled in with zeros. So maybe we could start with some suggested one by the designer, and then the first person just pays the difference between his and that.
Correct.
Would you end up at different allocations if you start with a different sort of profile?
Oh yes. It would be very different. Now this one is natural because we're gonna add extra things such as budget balance, non-negative cost shares, standalone test, things like that. But yes. And you will see when I describe a general family of incremental mechanism, it's fairly general. With the right assumptions on the cost. Now, okay, so this is weakly group strategy proof, and notice that if we are put off by the fact that it's very unfair in the sense that they have this fixed priority ordering, so if marginal costs are generally decreasing, it's very favorable to the last players or vice versa. But if you want to make it fair, just randomize. Just randomize the priority ordering. That's not going to respect group strategy proofness, but at least it's going to respect strategy proofness for any specification of your attitude toward risk. Because you know that the ordering is random. Okay, still you don't have any incentive to misreport. So the question then would be, how inefficient is that, and can we do better than that in some ways?
Sorry.
Yes.
Could it be manipulated by someone who has a Cybele, basically?
What, sorry?
Who has a Cybele, like a marionette?
You mean a clone?
Yeah, or someone. So he's pretending to be 2 agents, but it's really 1 agent, and then has at the end the summary, the sum of his.
That's I'm not considering this kind of manipulation. You mean instead of demanding x1 plus x2, he would try to demand x1 as x1 and x1. Here, especially the C function is not an additive form. I mean, if it's an additive form, I suspect that it would not be a problem. But if it's not in additive form, yes, these sort of things would be yes.
So you haven't made any assumptions on the C function yet? Right?
At this point, no.
Okay.
Except that I'm sort of assuming that this maximization problem have a solution, which is just nothing goes to infinity. But at this point, just to make this kind of statement, I assume zip.
Okay.
See, that's the point. Yes.
But if there's a random priority mechanism, then even if you want to act as two agents, it will not probably make any difference, because
Even if you wanted to.
if it's a random priority mechanism instead of a fixed order, then even if you try to act as two agents when you're actually one person, it should not make any difference, because.
Oh, then yes. No. You can then. You can. It's a little bit. I mean, I cannot give you the example off the top of my head, but you definitely can. Because when I am first and third, I can help you. No, it's possible. It's possible in a strict way. I mean, when I will be first before you, I will help you like this. When you will be first before me, you will help me like that. And because we have different utilities and so forth, it can very well. Yeah. Okay. And anyway, I'm not going to have to offer any systematic result about mechanisms which are random. I mean, any systematic characterization result by those. I mean, it's probably the most open part of this theory. Okay. All right. So the TU cooperative games, which is this first part, the purely axiomatic discussion of fairness, I'm going to skip because given the way I was holding to my schedule yesterday, I should be realistic, and I'm going to assume that everybody here has some idea of what is the Shapley value, or can look it up in Wikipedia really quick. Now, the only thing, let's see. The only thing I want to remind you, because it's going to be useful, are those type of propositions. If the game V is super or submodular, V, remember, will be my cost function or maybe my surplus function, but we're going to stick to cost function because you have to choose one or the other. If the cost is submodular, then the standalone core, and that's the core defined by the constraints that nobody should pay, the cost charged to any coalition of agents should not be more than the cost of serving that coalition alone with nobody else. The standalone core is non-empty, but moreover it is the convex hull of the marginal contribution vectors. Namely, if my here I'm talking TU cooperative game, so for each subset I give you a cost, and I'm assuming the TU's cooperative game is submodular, so I'm assuming C of S union I minus C of S is actually decreasing with respect to S, and in that case, if I take, for each priority ordering, if I take a list of payments which are precisely like here, C of 1, comma, C of 1, 2, minus C of 1, etc. So the list of this incremental cost, and each such vector is called a marginal contribution vector. So each such vector is in the core, and moreover, the core is the convex hull of those vectors. And the fact that the core is the convex hull of those vectors is characteristic of the submodularity problem. And therefore, the Shapley value is the center in the sense of average of all these extreme points, center of the core. And moreover, if we have a submodular game or a supermodular game, we can define solutions such as the Shapley value, which have this important property of so-called population monotonicity, which is that whenever you consider the solution for a subgroup of player S and the subgame restricted to those participants, and you add a new player, to the game, and you extend the value function accordingly, then in the case of the submodular, it's going to be a Pn minus, so then the cost the cost share cannot go up. So let me repeat that because here probably. So if we look at the again, if we have a submodular game like this, and this one Cs plus I minus Cs is decreasing in S, then we can define the Shapley value. Then we can define the Shapley value of this game, which will be a psi I of N and C. And then we can compare what happens to the share of agent I when, instead of looking at the set of agent N, I look at the set of agents N minus J C, where I'm just excluding agent J and restricting the cost function in the obvious way. I mean, it's simply that now I only have to consider coalitions which are included in N minus J, and they keep exactly the same cost function. So when I look at the new Shapley value after excluding J, then it will be greater than or equal. And this one is not smaller. So in other words, submodular cost means it's a good thing to have more people. It corresponds to decreasing marginal cost, so it's a good thing to have more people. If somebody leaves, that's bad news in general. And indeed, each individual person will feel that as a weak loss. So it corresponds to it's the same idea as population density in the lecture yesterday. And the theorem is that such things in submodular games, such solutions satisfying this property exist. The Shapley value is an example. Another one which is an example is the dot array solution, the one which selects the Lorentz dominant element in the core that we looked at yesterday, and many other. I mean, there is no general characterization of all the population monadonic solution there. I mean, for instance, you could take a convex combination of the Shapley value and the dot array, and presumably many other things. So, but such things exist because of submodularity. Okay. All right.
Wouldn't it be enough to assume subadditivity in some cases?
No, because the fact that you have a population monotonic solution like this implies in particular that each one of these cost shares is a selection of the core.
Okay.
And the core itself is not, the fact that you have subadditive cost does not guarantee that the core is non-empty. So even, and the fact that the game is so-called completely balanced, totally balanced, namely that the game and every sub-game has a non-empty standalone core, is far from enough to imply that such a monotonic selection exists. In fact, the existence of a population monotonic solution in a given TU game, one that would necessarily be totally balanced, is a very difficult issue. I mean, we know that it works for submodular or supermodular in the other direction, but we don't really know. It's very hard to characterize for what is the class, a slightly bigger class of games where such a solution exists. I mean, it's a tough issue. Okay, so I'm going to skip a bunch of straightforward applications of the cooperative game model and talk about the commons. So now I want to talk about the production games, and these games where the demands are elastic, and where the efficiency is to maximize this thing. And here you see, I'm going to start. Well, here I put the sum. I should have left it a bit more general. So okay. So now let's. I have to skip some things because I have just too many slides. Okay. So let's look at this model. So now I'm going to specify things a bit. So quite a bit. So IMC. This is the case of IMC is for increasing marginal cost. In other words, supermodular production. So the big distinction one big distinction in this theory is whether the marginal cost increase or decrease. Because it's only if we make one of these two assumptions that we have a good grasp on how the incentives can be organized, and we don't know much at all. The type of result I'm going to show, which are valid either when you assume increasing marginal cost or when you assume decreasing. I don't have anything to show, which would be okay. Now suppose you don't have either. It's either the marginal cost increase or decrease, and do both. I cannot say much at all. Okay. All right. So here is the first model. So first we're going to look at increasing marginal cost, which is for economists it's kind of the more standard idea of the commons. You know, it's the exploitation of a resource like a forest or whatever, where the returns to your effort go down as you want to extract more and more resources. And then we're going to look to the symmetric situation where marginal cost decrease. So it's a good news to have more and more people demanding output, and that's the situation which is more common in the context of network, sharing the usage of a network, because where the externalities are positive and so forth, and that's perhaps more familiar. In fact, the literature, the algorithmic and CS literature has been much more interested in the decreasing marginal cost for this reason, I think. Okay. All right, so the model is each agent demand, here I'm going to take discrete, you will see why. I mean, I'm going to use discrete for the thing, the utility UI xi. So I'm assuming, of course, that UI of xi is concave, right? I make the standard assumption of decreasing marginal utility. And the cost function is homogeneous. It's the cost of the sum of the demand, and it starts at 0 and it is increasing and convex. Okay. All right. So I spoke about that already. I mean, if I define a cost-sharing rule, that will define a demand game, and that's what I said at the beginning. So let's look at something a little bit more subtle than this incremental mechanism, but in a sense not too much more subtle, which I would call which I will call incremental mechanisms. So it's all deterministic. So it's something like this, but it's more general actually. If you have 3 agents, 1, 2, 3, it is defined by a sequence of the agents itself, a sequence in 1, 2, 3, which is arbitrary except for the fact that each agent should appear infinitely many times in the sequence. So it could be 1, 2, 2, 3, 1, 1, 1, 2, 1, 3, etc. Anything you want, but everybody will appear infinitely many times. And what it means simply is that this is the ordering in which we're going to offer successive units to the participant. So we have this cost function C, because the model is discrete, well, the cost function is described by marginal cost of the first unit, marginal cost of the second unit, etc. Right? That's your cost function. Remember, it's a homogeneous thing, so you just have to say how much it costs to produce 2 units, 3 units, etc. So you just have this increasing sequence of, this is the marginal cost. The cost of producing 2 units is C1 plus C2. Okay? And then the mechanism is simply to say, okay, agent 1 is here. Do you want to buy 1 unit? This is not to say that you are committing to 1 unit now. I'm asking, do you want at least 1 unit? If he says yes, fine, then I charge C1. I charge you C1 for now. And you are still in the game, but now, of course, I'm going to talk to somebody else, namely player 2. But if you say no, you are out. If you say no, you are out, and any time 1 would appear in the sequence, you're not there anymore. You're out of the game. But the others are still there in the same order as before, once I eliminate 1. So now I have 2, and I ask 2. Here I ask him, look, you have the option to buy 1 or 2 units. or 0, I mean 0, 1, or 2 units, what do you want? If he says 0, he's out. If he says 1, he's also out, because he has bought the first unit, but he declined the second unit. So he's out, but he does get his unit, and he pays C2, because we are after, the first guy has taken the cheapest first unit, so now he pays C2. And if he says, yes, I want 2, he's still in, and he has to pay C2 plus C3 for these 2 units. And we continue. And notice, of course, that if here, after player 1 was actually out, what we propose to player 2 would be 0, 1, or 2, but not at the cost C2 and C2 plus C3, but at the cost C1 and C1 plus C2. Right? So each time, it's basically like an assignment game, random priority, fixed priority assignment game where you assign unit one at a time, and each time you offer the cheapest available unit, right? So the cheapest object, which is okay, and so on and so forth. So the fact is that this, as a demand game, is very, very well behaved. Very well behaved. So look first at the first part of the statement. The resulting demand game is strictly dominant solvable. Its equilibrium is strong. It's also a collisional Stackelberg equilibrium. What do I mean, collisional Stackelberg equilibrium? It's this business of suppose, so you have the equilibrium, and you want to look at the following type of manipulation by a subgroup of agents. They switch to a different outcome, all of them. So if we assume that the rest of the agents do not move, the stability property we are looking at is that of strong equilibrium, right? A strong equilibrium is such that if I am at the equilibrium and several of us jointly deviate, it is not true that we are all better off, right? That's strong equilibrium. Stackelberg, collisional Stackelberg, which would mean we deviate, then we wait for the other to adjust, and the others, in fact, have a unique equilibrium in the residual gains after we moved and stick to that change, and after their readjustment, we are still not better off. Okay, same idea, but when you let them adjust to your deviation. Now, why is it so good? I'm not going to do, of course, the proof, but just to give you the idea, it's very simple. It's very simple. It simply has to do with the fact that the units you are offered are more and more expensive. So if you ever want to buy at least one unit, there is no way you're going to refuse the first two in the... sorry. If you decide to refuse the first, you would not have any incentive to buy one later on. So there would not be any incentive to cheat, to lie by saying, no, I take it and it's too expensive, I'm losing money right now, but later on I will be better off because I will get more units at better prices. That's not true. You will pay more and your marginal utility will be less. So if now it's not in your interest to buy this first unit at cost C1, it will never be to buy further units later on. So in fact, from the point of view of player 1, it is a dominated strategy to refuse the first unit if U1 of one unit is bigger than C1. If U1 of one unit is bigger than C1, it would be dominated to refuse. And similarly, if U1 of 1 is less than C1, it is dominated to ever accept anything. Because you're going to be only offered units at C1 or more, and therefore you should never accept it. Okay? So that's all. That's all there is to it, because you really don't need to know. you really don't need to know what's going on afterwards, whether your next unit will be offered at price C3 or C25, or it could be very, very expensive later, but as far as the first unit, you are sure.
This is a fixed priority, but would this not equally work even with a random priority?
I'll come to that. I'll come to that in a second. I mean, yeah, I mean, the short answer is yes, in the sense that, since each such mechanism corresponds to a strategy-proof revelation mechanism. I mean, if we were doing the revelation mechanism and then the random priority, yes, that would be perfectly fine. Yes, but instead of doing random interpretation, I will go to the continuous variant and limit. Okay. Now, the important part also of the theorem is the converse. Okay, namely, in this mechanism, you have group strategy proofness. Actually, I should have put weak proofness here. And the type of properties you have is that if you don't demand anything, you don't pay anything. No charge for no demand, which is, of course, a very basic sort of fairness assumption in this context, right? And you have what I call consumer sovereignty. I mean, it's the standard social choice terminology, that any agent can ensure some level of consumption. Any agent has a message, a strategy, which ensures a certain level of consumption. So, of course, here it's very obvious. I mean, if you look at this demand game and you have decided to buy 7 units and no more, you just have to wait your turn and you buy those 7 units at whatever price is offered. But this is also true in the revelation mechanism, because in the revelation mechanism where what you report is your utility, well, all you have to do is to report a utility where U1, so remember your U1, your utility U1 is also described by a list of marginal utilities, right? Marginal utility for, let's call it A1 for the first unit, A2 for the second unit, etc. That's your report of a utility, right? With the complexity assumption. So you simply report that the first number until 7, they are all bigger than the biggest cost you can. I mean, you have to keep the model a little bit bounded to make this kind of statement, but it's not very restrictive assumption. So you report a very high utility of the 7 first unit, and after that 0, and you are guaranteed that you will get to eat your 7 units and no more. Okay? So it's not the correct message, but it guarantees the consumption you want. Yes?
So I guess this is not robust to side payments within the coalition.
No. There's no side payments within coalitions in this. I mean, in general, in cost sharing mechanisms are very, very bad. I mean, they really eliminate. Most even in the purely axiomatic theory. I mean, if you try to enforce properties such as when the demand, a coalition cannot manipulate by artificially raising its demand, obtaining new cost share, and redistributing inside the coalition, you basically don't get any serious mechanism coming out. So yes, there are these kind of things I'm not allowing. Yes. Okay. So then the theorem says that if you look at a revelation mechanism which satisfies these things, I mean here there is a continuity assumption, then you have to do this sort of incremental mechanism. So this sort of priority structure, unit by unit, is in fact canonical, provided you impose those things. And the key step in the proof is, as I mentioned earlier, the fact that under consumer sovereignty and GSP, you can show relatively easily that your mechanism, which is in general a revelation mechanism, in fact must determine a cost-sharing rule. In other words, each time you give a certain list, you satisfy a certain, you implement a certain list of consumptions x1, xn, you must also implement the same list of cost share. And therefore your mechanism defines the cost-sharing rule, and then that's how the proof proceeds. Yes.
So in this mechanism, what do the agents have to know? Just that the current price they're facing and that the later one will be greater?
Right.
Nothing else?
Right. That's exactly it. And it's really because of the, this increasing marginal cost assumption. Okay, continuous model. In the continuous model, this leads immediately to the serial cost sharing formula, the one that was invented by Scott Schenker, and then after which he and I worked on its strategic and axiomatic properties. Because in the continuous model, what you are doing here, think of the continuous model as a limit of a round-robin sequence of units, and the units are 1, 2, 3, and 1, 2, 3, and so you give one unit at a time, and an increment delta. So each time now you have a continuous model, so everybody can ask any amount, which is a positive number, and so you have to define each time how much of the unit you are offering. At each step you have to say, okay, do you want how much do you want between 0 and 1 or 0 and delta? So if you let the round robin go and diminish the increment, and you go to the limit, you obtain the serial cost sharing rule. And of course the strategic properties are preserved. So how does it work? How does it work with the, so you have U1, X1 minus Y1, that's the utility of the agents, and then you have the C of X1, let's say X1 plus X2 plus X3, let's say. Okay, so initially we are offered very small amounts in terms 1, 2, 3, 1, 2, 3, 1, 2, 3, so small that really what we can think of is that for this, okay, let's assume, just to fix ideas, that initially your marginal utility is positive, so you do want something. You do, let's say that your derivative at 0 is strictly positive, and it's actually strictly bigger than C prime of 0. So the thing will start. You want to start, just to fix ideas. You want something, and if you are offered it at the cheapest price, you will get something. So when we start and we have very small amount, everybody is in. So let's say it's the same for not only for agent 1, but also for agent 2 and for agent 3. So initially, we start offering a small amount, and everybody is in, and everybody is paying what? Everybody is paying C of 3 delta over 3. If I have offered 3 times delta, and again, this is just making loosely the limit argument, you are paying C 3 delta over 3 to get the share delta. Right? And okay, so therefore you're going to be in as long as this is still worth it. So at some point when agent 1 is looking at, some agent is looking at UI of xi minus C of 3xi over 3, at some point this function of xi is going to start, is going to reach its maximum, right? So at this price there is a limit after which you want to stop. But notice that, and that's the point where, that's the latest point. That's the latest. That's the point at which you would be out if everybody else is still in, right? So therefore, if you look at the guy for which this xi is the smallest, this is exactly when he's going to opt out. Because since this xi is the smallest for him, it means that for the others, this function is maximum later. So as long as we didn't reach this quantity of 3xi star, we were still sharing the cost equally like that, and he was still accepting everything, and then after that he refuses and he's out. But you see that once he is out, now we have exactly the same situation between, let's say that this was agent 1, now we have exactly the same situation between agent 2 and 3, except that the incremental cost, they're going to divide in 2 instead of 3. So after this one, the next shares. So again, so let's say that we're going to have the demands x1, x2, x3. So the first guy is actually paying C of 3x1 over 3. That's the guy who decided to drop first, was the smallest demand. Now the second guy is paying what? Well, he already paid the same share of the cost up to 3x1, and then for the cost between 3x1 and between 3x1 until x1 plus 2 times x2, he's paying half of this incremental cost, right? So C of 3x1 over 3 plus 1/2 of C of x1 plus 2x2 minus C of 3x1. And then y3 is the rest. He pays that plus the last incremental cost. So this formula, this serial formula, which is a bit messy to read, but the intuition is very simple, comes out completely naturally from these incremental methods going to the limit, and of course it does preserve the strategic properties of the demand game. All these properties that I listed are correct. So incentive properties, so this is an analog, if you want, an analog of the previous theorem for the discrete context, except it's not exactly the same. The first part is exactly the same. For every preference profile of, here you actually, I was using in the discussion the quasi-linear context, but you can do much more general. You don't have to assume preferences to be quasi-linear. You can assume Arrow-Debreu preferences, monotonic, convex, and that works, because the serial demand game is going to be strictly dominant solvable, exactly the same property. And the corresponding revelation game is GSP. I mean, the trick here is that this mechanism will guarantee a unique Nash equilibrium, which is also strong, etc., for every profile of Arrow-Debreu preferences. Okay. Now, it turns out that the mechanism can be characterized with some extra little assumption by the property that it has a unique Nash equilibrium at every profile of Arrow-Debreu preferences. And here you really need the full Arrow-Debreu domain. It would not be enough. This statement is not correct if you require unique equilibrium, Nash equilibrium at all profile of, let's say, quasi-linear utilities. Because then I can use something as simple as the average cost mechanism, I mean, where you demand a quantity x1, xn, I take the total cost and I divide it in proportion to your demands, the simple average cost mechanism, and that one would have a unique Nash equilibrium at all quasi-linear utility profile, but not at all preferences coming from the general Arrow-Debreu context. I mean, there is here a subtle thing with the domain of preferences which which takes some work to explain, so I'm not going to do it. But, okay, all right. And notice also that in the characterization theorem, we have to assume smoothness, okay, strict monotonicity, and it's not, unlike the previous theorem, it's not a characterization on the unique GSP revelation mechanism such that It's a characterization of the unique demand game. So it's a characterization of the cost sharing rule. So it's a weaker result in that sense. And it's possible that, in fact, a stronger result directly on the class of GSP mechanism would be within reach, but no one. I mean, it's a hard question. See, to compare with the average cost demand gain, simple but very meaningful. Existence of the Nash equilibrium there is guaranteed in the Arrow-Debreu preference domain, because remember in the Arrow-Debreu what I insist on is complexity of preferences, so there is no issue to get existence of a Nash, but it is not unique in general. You have to assume something called binormality of preferences, of which quasi-linearity is an example. So uniqueness is often true, but even if it's unique, it is manipulable. So even if you say, okay, let's use the average cost mechanism, let's assume that utilities are quasi-linear, therefore I know that the average cost gain has a unique equilibrium, so I can look at that equilibrium as a revelation mechanism. Give me your quasi-linear utility, I implement this equilibrium. That is manipulable. That is not strategic. Okay. Neither is it a strong equilibrium or things like that. Nash equilibrium is not strong. So it's really it's clear that there is a unique character of this serial formula, which I think is very well explained by the result in the discrete case. Okay. So if there are no, there is a further things here with things like this. Where I want to go very fast, but for instance, you see, look at, just to tie up a little bit with the discussion of yesterday. One thing you can show in the equilibrium of the serial mechanism is the no-envy property. The no-envy property, which is false for average cost mechanism. I mean, in the equilibrium of the average cost mechanism, it's quite possible that when I look at my pair of my demand and my cost share, I would actually prefer to have your pair rather than mine. But here, for the serial mechanism, it is not the case. I mean, you don't have any NV, and that's one of the nice properties. And there are some standalone core properties and so forth. But now, very quickly, to mention a type of work that I have been doing on the price of anarchy for this class, for this model. It's a difficult question, I think, and here is what I can show. I mean, it's really the type of result which certainly is improvable. But so what are we looking at here? We are looking at the demand game of either the serial mechanism or the average cost mechanism. I mean, in the paper I looked at one or two other mechanisms, but these are the two main ones. And what I called price of anarchy corresponds to this ratio, worst ratio of equilibrium surplus to efficient surplus. So you see the gamma depends on n, the number of players in the game, C, the cost function, which is this one-dimensional convex function, and phi is the cost sharing rule, which here I'm going to take only to be serial or average cost. So, and I want to take this ratio to be the minimum of this, the minimum of this ratio equilibrium surplus to efficient surplus over all profiles of concave quasi-linear utilities. Okay. So it turns out it's rather interesting that for n equal 2, when you have only two people, you can make the case that average cost behaves better than serial in the following sense, that you look at power functions like this, and you see that the worst efficiency ratio of serial goes down to 1/2 when P starts at 0, I mean not 0 but strictly positive, and goes up to infinity, and the worst ratio, the serial mechanism for very steep marginal cost only captures 1/2 in the worst case, whereas for the average cost it actually goes in the other direction, and it preserves at least 77% all the time of the surplus in the worst case. So it's clearly better. But on the other hand, when you increase the number of participants, then the serial mechanism has a very strong advantage, because the worst efficiency, I mean, it's not that great. It's 1/log of n, which means that your equilibrium surplus could be as bad as 1/log n of the efficient surplus. So it loses quite a bit, but average cost loses even more, right? And I sort of conjecture that this lower bound is the best asymptotic price of anarchy for a demand game in which you require budget balance and non-negative cost share. Okay, so let's. All right. General supermodular cost is just a generalization of this kind of results to the case where the cost function does not take into account the sum of the demand, but some arbitrary list, but with the property that the second partial derivatives are all non-negative. And it's similar, but there are no really deep. I mean, the theorem of the characterization in the discrete model is the same, and the serial mechanism can be extended, but the characterization results are much harder. Okay, so I want to spend some time now on the submodular cost case. So we are doing exactly the same sort of analysis now, but except that now the externalities in the production become positive. So before, for this sort of model, what I had is more people is worse, it's bad news. I mean, one more user deteriorates the usage of the next unit, deteriorates the marginal cost for everybody. Now I take the opposite assumption that costs are submodular, right? And here the funny thing is, and it's really interesting to me, that the difference between the case where the demand 0, 1, a simple binary demand 0 or 1, and the case where you demand multiple units is very, very strong. And there is a very sharp distinction between the case where you demand 1 unit and multiple units. Sharp distinction which does not exist over here. I mean, here in this theory, for instance, the theorem of characterization with incremental methods, it applies also in the case where everybody demands at most 1 unit, where you have a single sequence 1 to n. So let's look first at the case where each agent demands 1 or 0 unit of service. So C of S is the cost of serving the people in coalition S, and the game is submodular. And we are interested, for the reason that will be obvious in a second, we are interested in cost-sharing rule, which satisfies this population monotonic property I was mentioning earlier, which is known in the literature more as cross-monotonic, and which means, I repeat, that when your cost share, when only a subset S of users is served, and you are one of them, your cost share is at least as large as when an extra user joined. Okay? And as before, we have these two examples, Shapley value, dot array, and others are possible. So in that case, the demand game. So now you see, it's a way of saying the demand game has very good strategic properties and will also induce a revelation mechanism with very strong, with the strategic proofness type properties. But the formulation is different. The formulation is different because it's a statement about the strong equilibrium of the demand game, not about the Nash equilibrium. The reason being that because you have submodular cost, it's very normal in those kind of game that in the demand game that you have a bad equilibrium, for instance, at 0. Because marginal cost decrease, it means that the first unit is the most expensive. So it's entirely possible that if everybody else is out and demands 0, you don't want to pay for the first unit. It's too much. But if there is enough people to share the cost and bring down the marginal cost and the average cost, then of course you will be happy to join. So you typically have good and bad Nash equilibria. The one that we want to look at is the strong equilibrium, which moreover is not unique, but there is one which is Pareto superior. And it's one that's easy to reach. It's one that's easy to reach because in view of the cross-monotonicity property, it's you obtain that strong equilibrium by a simple descending algorithm. A simple descending algorithm. Remember, okay. So you have your cost function and you have your agents. And since the demands are binary, everybody is utility is described by a single number, which is the willingness to pay for the service, right? Because it's either 0 or 1. So what you do is you start by asking to everybody, what would you accept to pay for service if your cost share was the lowest possible cost share according to my rule, namely the cost share when everybody is served. Remember what the cross-monotonicity says, that this cost share when everybody is served is the lowest you could possibly pay among all, depending on who is actually served. So at that price, you have to say yes or no. If you say no, you are out. If you say yes, you are still in, but it's not sure that you will actually get service at that price because probably some people actually did say no and we cannot afford to charge you this price. Right? So if you say yes, you are still in, and we look at the subset N1 of those who said yes. Right? If that subset N1 is actually N, if everybody said yes, we are fine because we have everybody on board, everybody is willing to pay this, we cover the budget, that's fine. But if not, we have a subset N1, and now we have to repeat the question, but with a higher tariff. Now we say, okay, suppose you have to pay psi I of N1 and C, are you still in or not? Okay? And so on and so forth. So it's exactly the same strategic idea as for the previous case of the increasing marginal cost, but in reverse, right? Because when you are offered a price here, you know that subsequent price can only be worse. So if you are still good at that price, you should stay in. But if your UI is already less than this, there is no point in hanging around because you will never be offered a better deal, right? So therefore, you can exit immediately, and you should stay. You should stay in if you can afford at this cheapest price, because you can always exit later if the price becomes too expensive. Okay? So etc. So you continue until at some point either you get an empty set or you get a set of N2 such that everybody says yes, and if everybody says yes, at that point you provide the service to these people at the corresponding cost. Okay? So, all right. So this defines definitively, just like before, regulation mechanism, which has all the strong incentive properties, and it can be characterized. I mean, this class of mechanism, because there is one such mechanism for every cross-monotonic cost-sharing rule. This class of mechanism can be characterized by the property of group strategic proofness, no charge for no demand, and consumer sovereignty. The same sort of, same as before. And it turns out also that's an interesting viewpoint on the Shapley value. It turns out also that in this class of mechanisms, if we want to discriminate among all possible cost-sharing rules satisfying this cross-monotonicity property, we can do it by a test of worst absolute efficiency loss. I mean, it's a price of anarchy type test, but not of the sort relative surplus, comparing efficient surplus to equilibrium surplus, because in fact that doesn't work in this type of model, but it's rather by looking at the worst absolute efficiency loss. Why absolute? You don't have to worry here about this absolute efficiency loss going to infinity, because it's clear that if you give me the cost, the technology, and utilities become enormous, so that everybody is willing to pay at any cost, including the most expensive, the cost of a single unit, then at that point, any sort of mechanism will become efficient in equilibrium, because everybody is willing to pay anything, so everybody says yes immediately, and that's the efficient solution. So therefore, the efficiency loss becomes zero if the utilities are large enough. So therefore, the absolute efficiency loss has to be bounded. And indeed, it is, it cannot go too far, but what you can show is that it is by taking the Shapley value that you get the smallest worst absolute efficiency loss. And the proof of that is rather similar in technique to the characterization of the Shapley value by Hart and Mascolel in terms of potential function. But for those of you who have some familiarity with that. But for instance, if you take the simple case where the cost of producing service involves a fixed cost plus a variable cost which is additive. So really the variable cost plays no role, because you're going to charge to everybody a share of the variable cost, but you're also going to charge a fair and equal share of the fixed cost among all those who are willing to participate. Then the worst loss you get is essentially log of n times the fixed cost. So, okay, so that's not too great, but that's not too bad. I mean, okay. But the funny thing is that it pinpoints to the Shapley value. Okay. Now, here I don't have time to go through this section. I mean, again, the slides are available and we can discuss them. But when we try to now go still in the supermodular cost to the case of multiple units, then things become really nasty, because even in the case where your cost function is homogeneous, it's the C of the sum of the demand, this time, when you look at the demand gain, existence of a Nash equilibrium is no longer guaranteed, even if you assume convex utilities, because now you have a concave cost function, so you are violating, the basic convexity assumption, so equilibrium doesn't exist anymore. Yes?
So what's the demand gain here? What cost sharing rule is it?
This applies for serial average cost, and in fact, I have a conjecture that you, let's see. Yeah, the conjecture I have is that it's impossible in this case, in the case where the cost of C of Cxi, it's impossible to guarantee existence of a Nash equilibrium by a cost-sharing rule which would be symmetric. I mean, it's possible, of course, if you do the incremental thing, because there we saw that it depended on no assumption whatsoever on the cost function. But if you want something symmetric, and of course which respects budget balance and non-negative cost shares, I don't know of anything, and I'm pretty sure it will not be possible. But okay, so I mean okay, so let me skip that part because I want to mention things which involve other people than my work and which are in fact closer to the to the algorithmic spirit of this summer school. Okay. Now here, but I want to say some things about the type of work which has been which has come up in the in the CS and algorithmic community, and which is in fact really taking a slightly different viewpoint with great efficiency to try to overcome some of the difficulties that you run, some of the walls you run into in the model I just presented with full budget balance and no compromise of that sort. Okay, so first of all, the first observation is that you have a number of important problems of combinatorial optimization in which, such as set cover, traveling salesman, etc., in which the cost function is going to be only subadditive and certainly not supermodular, and therefore it is out of the question to think of a cross-monotonic method to share the cost, because submodular cost, problems with submodular cost are rather special, and when it's not, well, you cannot hope for cross-monotonicity. And therefore, right. You can still use the trick of the fixed priority mechanism to define weak group strategy proof mechanism and still remain budget balanced, but we don't have, those mechanisms will be very unfair, and something like the random priority can be extremely inefficient. In fact, if you think of random priority in the case where marginal costs decrease, then it's typically a very bad mechanism. I mean, it's one with good incentives properties, but since you are offering to the first person the first unit at the most expensive cost, you have there is all the chances that this person will refuse, will decline, and then everybody after him will decline when there was in fact an important efficiency, an important opportunity of surplus, right? So there exists some characterization of weakly group strategy proof and budget balance mechanism. They are rather complicated, so I'm not gonna go through them. But the type of new idea which seems to be very promising is to actually relax the budget balance assumption. Okay, so in traditional mechanism design literature, you are concerned by two types of things. You would like to balance the budget. You would like also to achieve allocative efficiency, namely to achieve the level of demand which maximizes the total surplus, the sum of the UI xi minus the cost, and typically the literature focuses on one of these two criteria and ignoring the other, right? So the results I've been presenting are focusing on budget balance, imposing budget balance systematically and looking at strategy proofness, but not worrying too much with the fact that the equilibrium that results will not be will not give you the efficient level of production, and then maybe trying to evaluate, what's the loss. And symmetrically, if you look at the literature on VCG mechanism, which I'm not, of course, discussing here, but there the concern is with allocative efficiency. We guarantee that the right level of production obtained. We guarantee strategic proofness, but we drop budget balance. So, of course, in that literature, you can also do the operation of saying, okay, well, what's the minimal budget imbalance that we can achieve? But a more sort of global approach is the one that Tim has introduced a little while ago, which is to try to combine the two things of budget balance and allocative efficiency by doing jointly an approximate version of both. So trying to say, look, a general mechanism which is GSP is going to be approximately budget balance and approximately give you allocative efficiency, and maybe we can try to get some sense of what is the fundamental trade-off there, how much of budget balance we must give up to achieve pretty close to allocative efficiency and vice versa. And those results, which are still not very developed, in the sense of not very systematic, they seem to, they are really giving a new perspective, which should be very fruitful. If we can really get into the heat of it and understand, try to get some general results which are valid for all submodular cost function, all supermodular cost function, and things like that. We are not yet there. But I just want to show here. I still want to 1 minute. Yeah. Okay. Just want to show the type of results that you get. This is a result in the paper by Imorica and co-authors, where in the edge cover problem, you get a bound on the budget balance that you can achieve, the level of budget balance, if you insist on the cross-monotonic cost-sharing rule. Therefore, you preserve the strong incentive properties, but you lose a little bit of budget balance, and you can get as far as 50% of the budget balance. You recover at least 50% of the cost. Or you have a deficit which is at least twice the cost. It's not bad. It's not so bad. Then in other problems, set cover, there are other bonds. But now Tim recently introduced a generalization of cross-monotonic mechanisms, which he called the acyclic mechanisms, which are it's a very natural modification of the type of things I was presenting, because it simply uses the same idea of offering successive units at successive cost, which will be increasing, but in adjusting the cost share. So let me just finish with this example where you have 3 agents, cost 10, 12, and 24. These are the marginal cost of my function, right? So it's a U-shaped average cost, and you can see that the average cost is first 10, then 11, and then it goes up. So then you have Then you have utilities like this, 9, 7, and 5, and the efficiency is to serve agent 1 and 3 for a surplus of 4. Okay. Now the cross-monotonic mechanism here will simply offer C3 over 3. Sorry. The cost I wrote there are not the marginal cost; they are the total cost. So C1 is the cost of 1 unit, C2 is the cost of 2 units. So the average cost is 6. And C3 is the cost of 3 units. So the average cost is 8. So the average cost goes from 10 to 6 to 8. And that's why it has this U shape. Sorry about that. And so there is a surplus of 4 if you serve 1 and 3, but in the standard cross monotonic mechanism, where you offer them C3 over 3 equal 8 to all, then 2 and 3 decline, after which you offer C1 to 1, who declines, because C1 is 10, which is too high, and you have 0 surplus. But in an acyclic mechanism, you can do better simply by offering C3 over 3 to 1, who accepts, C3 over 3 to 2, who declines, but once 2 declines, now we know that we are only 2 people left, so we are offering again C2 over 2 to 1, and before saying anything with agent 3, so C2 over 2, 1 accept, C2 over 2, 3 accept as well, and you reach the efficient surplus. So it's a richer class of mechanism in which you are more subtle and more efficient in the way you make a successive proposal, but it clearly achieves better efficiency performance, both from the point of view of budget balance and the point of view of allocative efficiency. Okay, I have to stop.
And stop for the wonderful talk.
Thank you.